All right, let's take a look at question 17. In question 17, we're going to see the relationship between discrete and continuous exponential growth models. All right. Question 17 reads, a savings account S has an initial value of $50. The account grows at a 2% interest rate compounded n times per year, t, according to the function below. So we have the growth model right here. Okay. Question, which statement about the account is correct? So before we get started, let's go ahead and explore the relationship between the discrete and continuous exponential growth models. All right, so you definitely want to know both formulas. Now, discrete basically means a specific period of time. You compound for a specific period of time. So like n times per year means discrete n times in a year. All right, so exponential growth models, we're going to start with the discrete case. Exponential growth models, if we have the discrete case, basically n times a year, the formula in that scenario is y equals the initial amount times 1 plus the growth rate over n raised to the nt. Okay, so if it's n times a year, like if you have it one time a year, if you have it twice a year, biannually, or quarterly, 4 times a year, monthly, right, 12 times a year, or daily, 365 times a year, that's what you have, a discrete scenario. Okay, continuous basically means that it is constantly compounding. Every fraction of a second is constantly compounding. In that case, your formula is going to be y equals the initial amount times the natural number e raised to the rate times time. Alrighty, so these are the two models. Now, are these two related? Guess what? They certainly are. Alright, so what you want to note is the connection between these two formulas. So what you want to note is that as the compounding period n gets infinitely large, okay, so what is the biggest number in the world? The biggest number is infinity, right? So as n gets infinitely large, basically as it increases, like it's talking about every second and every fraction of a second, every fraction of a fraction of a second. So as n gets really, really large, guess what? The formula on the left, y equals a times 1 plus r to the n, is basically going to become this formula right here. The discrete becomes the continuous. That's why they have their names, discrete and continuous. Okay? All right. So this one on the left is for n times. All right. A known discrete period of time, for example, 3 times a year, 4 times a year. And then this model on the right is continuous. All right, the time interval is so large that you cannot ascribe a number to it. Okay, so you're getting really, really, really small, so it's broken into infinite number of times, so n is very large. All right, so let's keep that in mind as we attack this problem. Let's take a look at option number 1. We're looking for the statement that's correct. It says as the value of n increases, okay, so n is going to infinity, the amount of the interest rate per year decreases. So the interest rate per year is basically our r value. Ladies and gentlemen, the rate is fixed. So this is false, okay, because the rate r is fixed. The rate is independent of n. No matter how big n gets or how small n is, the rate is always a rate and is fixed at 2%, which is equal to 0.02. 2. So whichever equation that you use, the rate value is fixed. All right, so this statement is incorrect because the rate doesn't change. Wrong. Number 2, as the value of n increases, okay, n going to infinity again, the value of the account approaches s of t equals 50 e. Oh, we have that natural number e again raised to the 0.02 t. Ladies and gentlemen, this is the correct answer. How so? Well, let's take a look at the two models we have. The first one, s of t, which is equal to 50 times 1 plus 0.02 over n raised to the nt. This formula tells us that the starting amount A is 50, the rate is 0.02 in decimal form. Okay? Now, this formula is consistent with which of these growth models? It matches the discrete growth model perfectly. Okay? Now, what did we indicate earlier? We said that as n goes to infinity, or as it increases, guess what? This formula is going to become the continuous formula. So let's write this formula, and the continuous format using our a and r values is going to be y, oops, not y. In this case, they're using s of t for the output notation. Is going to be s of t equals the starting amount, which is 50, e raised to the rate, which is 0.02 t. And that is exactly what we have here. Okay, this is the continuous growth model. When you take the discrete growth model and cause n to increase forever or to approach infinity. Alright, so this basically highlights the connection between a discrete and a continuous growth model for exponential functions.